Also want to thank so many of you for staying all the way through. This is awesome. And I don't think anyone asked this question yet. So for whom is this your first PaleoFest? Let's see a show of hands. That's awesome. That is great. Let's see, is this working? Because it's not mine. So I actually went back and I checked, and this is my 9th PaleoFest presentation and my 10th PaleoFest. Now I've done other events with the Burpee before, and that's why my count was getting off. Like the 2005 Tyrannosaur conference, and there are some other ones in there. In the year that it was the Women in Paleontology, I didn't give a talk for obvious reasons, but I did do children's programming. So I was part of the PaleoFest, but I wasn't one of the main speakers. So these are my previous cover slides, sort of a theme in some of these. But all right, and I thought about what I would speak about for this particular PaleoFest, especially given it's the 25th anniversary of PaleoFest. And so I thought a retrospective would be really important. And I think the Broussadis have gone. Oh, you're here? Awesome. Yeah, because I want to say awesome. Yeah, well, actually, I did want to actually address your parents here, because I wanted to relate it to because people have been picking on Steve throughout the meeting, but honest to goodness, think about that. Some great parents bring some kids who are interested in the subject to this, and within a decade and a half, he is one of the world's greatest paleontologists, and is going to live on in the history of our discipline for his own accomplishments and the amazing students he's taught. So who knows how many of the young folks here who have been brought in by their parents to see this may have equal contributions in the future. And that's awesome. That's really an important thing. It's also the second, well, we're into the third decade now of the Burpee working in the Hell Creek Formation. You're just into that. So I thought I would do a talk that was about contrasting two different specimens collected from it, but really I decided to be more of a retrospective of the research that's been accomplished because of what the Burpee has been doing in the specimens they've been collecting there. So I wanted to first of all, recognize some of the other the BLM under whose auspices we've been collecting out there. Our sister institution out in Ecology, Montana, Carter County Museum, all the various members of the Burpee Summerfield seasons, many of whom are here, that have contributed to this. And the Carter County research has been supported by lots of different groups and people, some of whom are in this room right now. And also wanted to point out that the land upon which this research is being done, this part of southeastern Montana is really has been a cultural crossroads of many nations throughout history. In fact, Medicine Rocks, which is right nearby, has been a really important part of many different cultures who have lived in that region and still do, and it's still important to them. So I just want to make sure we recognize that. So I've been saying, southeastern Montana and Ecology, but just in case you don't know, the research that the Burpee has been going on is right about here. The grape color here is the Hell Creek, is the current exposures of the Hell Creek formation, and these are the rocks from the very end of the age of dinosaurs, from the later part of the Maastrichtian age of the late Cretaceous epoch. And this is actually from one of Steve and colleagues' paper from, oh my God, 7 years ago, 8 years ago. Oh, wow. Well, anyway, showing some of the characteristic assemblages of organisms towards the end of the Cretaceous and then the beginning of the age of mammals. So, we see these wonderful, elegant creatures, and then rocks fall out of the sky, and we got the stumpy fuzzballs. That's okay. Some of my best friends are mammals. But yeah, the Hell Creek documents this last phase of the giant dinosaurs. Dinosaurs, of course, are still with us. They numerically outnumber us mammals in terms of species diversity, as we saw shown in the last talk. So the Burpee has been collecting a great number of really important fossils from these localities. Here's the Smithsonian mount of a cast of Ernie, went on display with the new Hall of Deep Time back in 2019. So there's a Burpee specimen swimming around in the Smithsonian. And of course, Homer, the most complete of the juvenile or subadult Triceratops found so far. And a whole plethora of turtle fossils, and there's mammals, there's fish, there's even invertebrates for invertebrate fans that have been collected. But really a lot of the hype about the Burpee's discoveries has been about one particular theropod dinosaur, and another that we've been working on for many years now that hopefully we'll have a lot more studies of in the future. These are respectively Jane and Pearl. I tried to scale these as close as I could to relative size. So you all know Pearl, we obviously don't have a mounted skeleton of yet. But Jane's tibia length is 840 millimeters. Pearl is not insubstantial, it's 685. Now, that said, if you saw Dr. Zano's presentation last night, she talked about an earlier member of the same group of Oviraptorosaurs from earlier in the Cretaceous in Utah, whose tibia, whose same bone, is 1,000 millimeters, is a meter long. So that's longer than Jane. Picture how big that animal was. So I'll actually get back to that as one of the stories at the end. So now I wasn't involved with the Burpee Museum back when Jane was discovered. And in fact, this story, talk to Scott about it. So here's Jane Ridge out there in the Hell Creek of Carter County, and they came across this wonderful specimen of a large theropod, medium-sized theropod dinosaur. And they found skull elements and postcranial elements, and they weren't certain at first what it was. And in fact, that's how I sort of got into the story, was it was probably the 2003 SVP meeting. Scott and some of the others from the Burpee said, hey, we've got this interesting specimen. You want to check it out? And they showed casts of some of the skull bones. It said, it's a Tyrannosaur, and it's smallish. We want you and others, they had invited Thomas Carr to check it out and other researchers to come in and look at it. And so in the spring of 2004, I came out. This is the first time I ever came to the Burpee and began looking at the specimen, the wonderful quality of preservation of the skull bones and the limb bones and so forth. Really intriguing animal. And the first big question people wondered about this specimen is, what is it? Now, there's been a lot of research on this since, so I did a Google Scholar search on the specimen number rather. I actually had to do it twice because some people will cite it as BMRP space 2002, and others as BMR space P 2002. And I did the Google search using this one first, and there were some papers that I knew existed. I didn't imagine these papers that weren't there. Check it. But 82 papers so far have been published that have actually cited Jane within the research. Not always as the primary focus, but in some cases very much so. And as I said, one of the first big questions was, what sort of tyrannosaurid is Jane? And the primary hypothesis that many of us have converged on is that it is the best juvenile specimen of Tyrannosaurus rex ever found. Yes, it is distinctly different in proportions, in skull shape and so forth, than a classic fully adult Tyrannosaurus rex, but allometry happens, ontogeny happens, we expect changes to happen. And based on previous work by Thomas Carr and others, there were a lot of attributes of previous specimens that have been considered something else that turned out to be most likely specimens the juvenile specimens of Tyrannosaurus. Of course, there is the alternative hypothesis, and that is that there is a second Tyrannosaurid in the Hell Creek, a smaller, more lightly built one. This is not a crazy hypothesis. It's certainly worthy of study. This second one has been given the name Nanotyrannus lancensis. This is the type specimen, which is just a skull that's been somewhat deformed by crushing. It had one advantage that this specimen, the Cleveland specimen, has over Jane's. It's got the brain case. And there are other specimens that are allegedly, at least by some people, representatives of this Nanotyrannus. This includes the so-called dueling dinosaur specimen that Lindsay Zano's crew now has in their collections and will be the centerpiece of a major research project. And a specimen from private collectors in the Palm Beach Museum. How complete the specimen is, how much of it was found in one location, I don't know. Never described in the literature. My main knowledge of it is I saw it on a TV show once. But it's been proposed, at least, as another member of this. Now, I'm not going to talk about the detailed research that has gone on to at least strongly suggest to many of us that Jane is indeed a subadult Tyrannosaurus. But that was actually the subject of a whole documentary. A documentary that was filmed in 2005, came out in 2006 by Brave New Pictures, The Mystery Dinosaur. As I say, the mystery is, why am I a Spinosaurus?
Probably.
Anyway, and of course, a Spinosaurus, a dinosaur about which we agree about so much. But that said, Jane has been included in essentially every modern study of Tyrannosaurus ontogeny because it potentially does represent one of the best representatives in one particular part of the growth sequence. So here is from Thomas Carr's masterwork on Tyrannosaur ontogeny, where he has taken 1,800 different discrete morphological characters and mapped them out on as many Tyrannosaur specimens as he could study in public collections, and reconstructed a reasonable sequence of transformations that the body goes through from a small form to the classic full adult like Sue and Scotty and so forth. We still don't have hatchling Tyrannosaurus, but they're out there somewhere. But here's Jane on the sequence. And so Jane represents, if these growth curves are accurate, the beginnings of a rapid phase of growth, essentially the beginnings of puberty, of the massive change from a smaller body form to a much larger body form, going through transformations of the skull shape, of limb proportions, and so forth. But exactly how old was Jane? Well, that's been the research of a couple different studies, most recently and comprehensively by Holly Woodward and colleagues, and some of those colleagues are in this room, using histology and counting these lines of arrested growth. Now, at this point, I think we all are pretty familiar with not only lines of arrested growth, but actually how we sample them and so forth. And the results from the Woodward et al. Paper was that Jane seems to have died in about her 13th year of life, or after her 13th year of life, so between 13 and 14. They had to retro-calculate back to get missing growth rings because they don't find the whole 13 because of the growth on the interior of the bone, the reworking and so forth. But this seems consistent. It's slightly older than was first approximated, about 11. Looks like it's about 13. Of course, one of the most interesting things about Tyrannosaurs is they've got nasty, sharp, pointy teeth, which they use to bite stuff. Or at least they used to. And one of the big questions, and it's a fairly large research field of figuring out how nasty were the bites of fossil organisms. And it's not just because we think it's really cool to think about creatures biting other creatures. Although it is. Those of us who work on carnivores. But no, it actually is First of all, an ecologically important aspect of an organism. How much force can they generate on potential food items, whether they're predators or herbivores, because they can determine what their food sources were. And it's a system where the mechanics are pretty well understood, and where the parts of that system, or at least substantial fractions of it, are preservable in the rock record, in the fossil record. And so, not surprisingly, it is a system that a lot of people have studied. And so one of the first studies looking at Jane's bite force was about 2.6 to 4.0 kilonewtons. That's a bite of something like 600 to almost 900 pounds. The Bates and Falkingham team found that as an adult, a big adult T-Rex, much more massive bite, something like 35 to 57 kilonewtons. That's up to about over 12,000 pounds. But this isn't the only thing people have been looking at with regard to bite force. So here's Peterson Dowse's study looking at T-Rex or potential small tyrannosaur bites on the Triceratops bones found in the same formation, matching about the size of Jane. Rowan Snively's recent work looking at the bending strengths of the jaws of various dinosaurs, and Jane is right there. And of course, Evan Johnson Ransom had this brilliant presentation earlier, the first day of the meeting here, of his ongoing research on bite forces of Tyrannosaurs, not merely looking at individuals, but both ontogenetic changes and phylogenetic changes, which of course is the big question. Yes, it's really cool. We get a number and it says this animal can exert this much force, but really, we're scientists. We're trying to put it into a broader context, both the evolution of traits and the transformation from birth to adulthood. And it's more than predation involved. Peterson and others described back in 2009 some trace fossils of tyrannosaurs on Jane, that is potential bite marks on the face of Jane from another Jane-sized tyrannosaur. Roughhousing behavior in tyrannosaurs. Now, this is not a novel discovery. We have seen in many long-snouted carnivorous dinosaurs face bites, non-fatal face bites. So, much like monitor lizards or crocodilians, when they were with each other, they were playing around, maybe fighting over food, maybe just, I really want to be in that spot. You're in my seat, basically. And who knows what else? It could even be precursors to learning about courtship behaviors. We could see the evidence of the bite in the form of bite marks, but understanding the behavior is more difficult. But moving away from the head, you've all seen how long-legged and lanky Jane is, and this specimen was part of a whole assemblage of theropods that a team I was involved with looked at in trying to reconstruct the agility of carnivorous dinosaurs. Now, based on other lines of evidence, including the particular and peculiar morphology of the feet of tyrannosaurs and some other carnivorous dinosaurs, there was the hypothesis that they were well adapted to turning. That is, they were relatively agile. And so we had a project where we were trying to reconstruct agility in carnivorous dinosaurs, and I didn't want to go through all the math in here, but basically we took dinosaur reconstructed bodies, used them as sausage slices, so we sliced them up, basically figured out the volume of each slice, and figured out the density distribution of the bodies in the slice to get a sense of how resistant the body was to turning, so rotational inertia. And then we tried to figure out the torsion available, the torque that can be put on the body from the muscles of the pelvis and the muscles running from the femur, the thigh, onto the tail. These would be the main muscles that would generate the turning. And coming up with a metric that would be an estimate of relative turning ability. And we found consistently that tyrannosaurs, in blue, had a higher agility, a greater ability to turn than did other types of carnivorous dinosaurs of the same body size, and those are lumped together here in red. And just to show you, Jane is up here. Now, Of course, as with most cases, smaller individuals, this is body mass down here, smaller individuals are a lot more agile than the big ones, than the adults. And so, Eric Snively and I like to refer to Tyrannosaurs as the ballerinas of doom. And Jane is a good example of that. And I've had a long interest in the ecology of carnivorous dinosaurs, and particularly ontogenetic, that is, growth changes in the ecology of dinosaurs. And Jane was a great specimen to incorporate in that, because she gives us a real sense of what the body shape is like, what the teeth are like, what the forelimbs are like of a mid-sized tyrannosaur. Now, it's well known that a big Tyrannosaurus, the creatures on its menu, would presumably be primarily the other big dinosaurs of its environment. Duckbills like Edmontosaurus, horned dinosaurs like Triceratops, and if it really needed some roughage, Ankylosaurus. That a lot of the other creatures in its environment might be too small for it to routinely get, at least as an adult. But young Tyrannosaurus, like Jane, has got no good chance of tackling an adult Edmontosaurus or an adult Triceratops. The individuals who tried to do that did not become adult Tyrannosaurus. But there's a lot of other creatures in their environment that were probably too small and agile for the adult Tyrannosaurus to prey on a regular basis, but that a younger Tyrannosaur could. And these would be the ostrich dinosaurs, and the domeheads, and the smaller ceratopsians, and Thescelosaurus, who never gets a break. And of course the juveniles of Edmontosaurus and Triceratops and Ankylosaurus. And so I and other researchers have talked about the possibility how smaller tyrannosaurs occupied the otherwise missing middle-sized predators in the environment of Lyramidia, the late Cretaceous of Western North America, that in earlier generations, earlier times of dinosaur history, were occupied by mid-sized predators, including the early tyrannosaurs. And it's worth noting there are other types of changes that we see going on in Tyrannosaurus as well. So Jane does not have long arms by any stretch of the imagination, but proportionally, they're much longer arms than we see in an adult T-Rex. Jane could potentially clap her hands. This is something an adult Tyrannosaurus could not do. Okay, we haven't actually seen it come all the way in, but it looks like they could actually touch hands together, whereas a big adult T-Rex, that's out of the question. So it might be that the answer to what tyrannosaurs did with their forelimbs was something different when they were young than when they were adults. And this is just comparing, this is the the humerus, the upper arm bone of Jane, compared to the upper arm bone of the specimen Sue, one of the largest specimens, the one on display at the Field Museum. So yes, their arms continued to grow throughout their life, but the rest of the body grew faster. And that's true of many different traits in Tyrannosaurus. So here's a very young, actually younger individual than Jane from a Saskatchewan specimen of T-Rex. And here is the maxilla of the same bone, although this is the inside of Scotty, one of the largest T-Rex specimens, and reconstructed versions of their skulls. So, and actually I gave the punchline to this one already. So work by myself and by Kat Schrader and colleagues suggesting that in Lyramidia and the late Cretaceous, that young tyrannosaurids basically occupied the middle part of the predatory guild. Okay, that's a little overview of Jane. A heck of a lot of research that's been done on that specimen already, and more that continues to be done. But there's a second cool theropod that we've been collecting from the Burpee digs in the Hell Creek, and that's Pearl. So summer of 2013, I'm actually out there in the field working with the Burpee crew, and same sort of spot. There we are. And Mr. Simpson, are you in the room? He's here. There you are. Yes, yes. Didn't want to be tied down in one place while we were digging. Likes to go prospecting, and went over the hill, and then over another hill, and I think actually another hill than that. That's right. From where we were doing digging up turtles and stuff, and came back that day with some theropod bones. And all right, cool. Let's go check it out. So when I say over the hill and over the hill and over the hill, let's see. So the Ninja Turtle site that many are thinking, that's part of the same ridge, so that's about over here. And so you have to drive around, go over this hill and down the gulch and over this hill and over around here, and there's the site. So over here, up and over, up and over, up and over, down and around and up, and then here we are. You can see this is from a later year. We've already dug into part of the hill and got the tarp up and are looking for parts of pearl there. So the next day, Scott and I and a few others, we'll see pictures in a bit, went out there to check out some more, and we're digging around and saw these bones sticking out. It wasn't just a couple isolated bones. There's something else down there. And work a little further. There's some toe bones. There's the tibia. So the shin bone and so forth. And Scott's super happy there. And I was super happy. Especially at one point, I'm digging in this one area. I see this end, and my brain for some reason was interpreting this as the end of a vertebra. And so I was looking at it, and all of a sudden it begins to slip out. And I'm like, oh crap. Because theropod vertebrae, especially at this point of theropod history, are extremely hollow and break apart easily. But it turns out, no, it's a claw. Yes. And so the reason it slipped out actually was a little bit of vegetation that got in there to occupy the space in between. What's even better is, hey, I've seen claws like this before. So I was happy. It was a claw. I was happy because, it's a claw of a creature. And so there's some of the other people. Another person of note, you should get him out to speak at PaleoFest sometime. So that's Jack Horner and Goodwin from UCal Berkeley as well. We were out there digging them up. Later on, we continued to dig some more. This is some of the sites. Found things like, these vertebrae. It's really, you can see, look at how hollow this is. It's all got sorts of chambers in it. That's why I was so scared when it came apart in my hand, only it didn't. And you named it Pearl, after Pearl City. There's a specimen over those little long bones of the foot, the metatarsals, which made me extra happy because I did my dissertation on theropod metatarsals. Yay, happy. And we continued to dig it up over the next couple of years. We've still, not all of it's out probably, but we still got to go back and check. The hole into the cliff, it went more and more. But seeing that particular toe, and then later on the metatarsals, indicated to me what sort of creature it was. And it was this totally unnamed creature that we've known about since the 1990s. It's got a name now. But it didn't while we were digging it up that summer. And it was a type of Oviraptorosaur. I first saw the bones of this, or this cast of this, on the desk of Phil Curry up in the Royal Tyrrell Museum back in the 90s. So we knew that there was a giant, at least what we used to think was a giant Oviraptorosaur, an ostrich-sized Oviraptorosaur, one of these beaked members of the carnivorous dinosaur group that lived in the latest Cretaceous of North America. Actually, bits and pieces of this had been collected for years and years and years beforehand. It's just no one knew what to make of those. So, you can go to some older collections and they're labeled like Carnosaur or, Theropod Indet. And it turns out I had been next to a footprint of one of these theropods before. This is the Zerps tracks from the Lance Formation of Wyoming. This is when they were still in the ground. This was back in the 1990s when I was digging with some of the folks from University of Pennsylvania. And yes, I had purple jeans. Thankfully, was never exposed to gamma rays because you wouldn't like me when I'm angry. But yeah, at the time we're saying, what is this track? Is it a young Tyrannosaurus? Maybe, But this is almost certainly based on its proportions, an Oviraptorosaur, one of these late Cretaceous Oviraptorosaurs. And so, some of us here, and Katie was not, have been working on this specimen for a while. Now, this creature had been known in the literature for a bit in the early 2000s as referred to Coniferae kerastenoides or Cananeatus, two previously named Oviraptorosaurs from slightly earlier in the late Cretaceous. And specimens have been collected by various researchers through the years. But while we were beginning to dig Pearl out, finally this dinosaur got a name when this team finally described the taxon and gave it the name Anzu, Wily Eye, and the nickname the Chicken from Hell. And there was their reconstruction of it. And so yeah, this was the same creature that we were finding that had been given the nickname Pearl. Now, they had a lot of the skeleton based on 2 different individuals that had been collected, and much of the skull and so forth, but they lacked certain elements. For instance, they lacked most of the toes, they didn't have those metatarsals at all, and there were some other bones that were missing from Anzu in the initial description. But Pearl fills in some of those gaps. And so it's providing new information about this particular taxon. So what's in white is what was done, this was some years ago, of our specimen, the one specimen here. And we're still again collecting more, like a really good pair of metatarsi, so both feet. And the toes on them, we're still finding toes. A wonderful ischium. Ischium was already known, but this is a cool specimen, so we want to show it. And so yeah, it's a member of this group, the Canaanathidae. Or Caenorhabdidae, either way, they don't care. It's a group of oviraptorosaurs, but unlike the really deep-billed oviraptor and its closest cousins in Oviraptoridae, these guys tend to have these longer, more slender lower jaws, and they had this pinch-footed structure, this arctometatarsus, which tyrannosaurs have and ornithomimid dinosaurs have, and so forth. Now, there hasn't been that much work published on Pearl yet, in part because we're still digging it up, and I'm sort of slow about getting that paper put together. But it is being studied by various researchers, and Jake Simon and Dave Evans described some information about Pearl at the Society of Vertebrate Paleontology meeting last year. Now, their paper isn't finished and published, so I can't give you all the details, and I'm not going to show you any pictures of it. But I can give you the punchline they had from the abstract, because that's fine and that's sort of fair game once the presentation is made, and that is, Pearl was a subadult too. Pearl is not an adult Anzu, and in fact, no one has, as far as we know, an adult Anzu. It was, based on the histology, Pearl was still growing at the time of death, as were the other specimens of Anzu that Jade has studied. So, how big did it get? That's a question we don't know the answer to. And oviraptorosaurs have this nasty habit of not having teeth. So at least with other animals, we might be able to find teeth that, we find a specimen of a subadult and we find its teeth and we see really big teeth from the same sort of animal. We can guesstimate how big. These guys don't do that. So we don't know. And, you might be wondering, well, it's an oviraptorosaur. How big could they possibly get? Well, and this is one unfortunate, so Anzu was, there's a long history of Anzu not making it into the press for a long time. As I mentioned, it was being studied back in the late 90s. And so we all knew that there was this big oviraptorosaur that was going to be a big one. And then I heard, oh, there's a paper coming out about a big one. And I reviewed the paper and said, oh crap, this is not Anzu. This is something that could pick up Anzu, at least a pearl-sized Anzu, and throw it around. And that's Gigantoraptor. Now Gigantoraptor is from Asia. It's older than Anzu. It's earlier in the Cretaceous, but it is a giant oviraptorosaur. And in fact, creatures like Gigantoraptor had actually been known for a while, but not from their body fossils. They've been known from eggs for decades. There were giant theropod eggs from Asia, from the Cretaceous, that in fact were sometimes marketed as Tarbosaurus eggs. And the logic went, they were clearly theropod eggs because they were similar to the eggs of oviraptorosaurs. But they were gigantic. What's another gigantic theropod that's known from the late Cretaceous of Asia? Tarbosaurus, East Asia's version of Tyrannosaurus rex. Well, it turns out no. These are oviraptorosaur eggs. They are eggs of a creature like Gigantoraptor. We have many nests and eggs of this sort. Here I am standing in a cast of them at the Maryland Science Center, and in fact they are arranged in this sort of pattern, and in fact with a space in the middle, because these were brooding animals, and it looks like the space is where mom or dad, and that's a whole other subject, sat down in the middle of it. And we absolutely know that these are giant oviraptorosaur eggs because sometimes the babies are found in them. This is another set of these eggs from China, and they gave this dinosaur a name, Big Elong, sort of baby dragon. And yeah, this is something really darn close to Gigantoraptor, and they actually be the same animal. It's hard to tell because if you only have the babies of this one and you have the adults of the other, but that's another story. But at least we know we don't have creatures like that in North America. Oh wait, we do. Now, these are older than the Hell Creek. These are, in fact, not that much younger than the fossils of Gigantoraptor in Asia. So these are from the Wayne Formation of the mid-Cretaceous of, in this case, Idaho. Eggs comparably big to those Gigantoraptor-style eggs. So yes, the mid-Cretaceous of North America at least had stalking around it Gigantoraptor-sized oviraptorosaurs that I would say we don't yet have the bones of, although, as we saw, the Zano team and Makavicki have bones of something in that scale, not quite this big. We don't know how old that individual was yet. So there's a lot more going on in the world of dinosaurs than we thought before. We're always finding something new. So the work continues. We do need to finally wrap up that quarry eventually when, nasty pandemics interrupting research and so forth, and I need to get off my butt and finish measuring all the bones and writing them up. That'll happen eventually. And so I thought I would wrap this up with sort of general retrospective thoughts. So first of all, science. Science is collaborative. There's a tendency, especially in some aspects of the news media, of really focusing on like the lone wolf who's discovering things. That's not the way we do things. We learn more when we learn together, and none of us knows everything. And that's especially true of techniques and methods. The people who know how to write the proper R code may not actually know the issues with regard to some other aspect of the anatomy and so forth. So we've got to work together to get these things done. And it's accomplished stepwise. There's never going to be a final word on any subject. We learn new things, we progress, we make new discoveries that builds on and adds to, or maybe even corrects previous work. Like, sorry, Carr's not here, is he? Yeah. Like maybe someone will show us that Nanotyrannus is real. Maybe. Honest to goodness, it's not outside the realm of possibility. Don't think that's the horse to bet on right now, but that could change with new information. That's how science works. And one of the most critical institutions involved for doing science is museums, because museums are essential for the preservation of specimens and the information about specimens for future work and future generations. And as everyone here knows, so I'm preaching to the choir here, it's essential to bring the wonders of the natural world to the public. So with that, I'll answer any questions and hope you enjoy PaleoFest 25. Oh, on the Gigantoraptor age studies. I'm trying. Steve, do you remember if anyone's done no lag studies on the Gigantoraptor specimen? Or anyone else? Does anyone else heard? I don't think anyone has. Yeah, that's a great question. A great question and a good topic. Yeah. Yeah.
Speaking of mysteries, have we come any closer to determining what exactly was the ecological role of, the niche of oviraptors?
That's a great question. The question is, have we come any closer in answering what the ecological role of oviraptors are, oviraptorosaurs? There is work in progress for various people, so I don't want to, I'm careful of not saying too much. But what I will say is there's more than one role, because there's actually quite a variety of styles of being an oviraptorosaur. So there's already been published work looking at the bites, for instance, of oviraptorids, which have these really short, squat, deep skulls, as opposed to the caenornathids, which have these longer, more slender lower jaws. They actually have some interesting things going on with jaw mobility that we don't see as much in other theropods, especially. They're not just doing this, they've got some other issues going on. There's been a question, one thing I can say, because we talked about it in our poster, is Anzu is unique, is unique among theropod dinosaurs with this pinched foot, with the arctometatarsus, by not plotting with tyrannosaurids and ornithomimids by having an extra long and slender foot. It actually scales on the same pattern that your average Joe Blow theropod plots on, Allosaurus, Ceratosaurus, etc. So it's not doing anything super special, even though it's got that arctometatarsus. There have been suggestions that maybe some of these caenornathids were like, honest to goodness, swamp dinosaurs. That they seem to have particularly long toes. And that maybe, we tried to say keep the dinosaurs out of the swamp, but something lived there. There were dinosaurs that lived in the swamp, so that's a possibility. Whereas, oviraptorids, we know that some of them are common in really arid environments as well. So, and as to what they were eating, good question, but presumably something softer probably than oviraptorids did. Yeah.
Maybe this.
And then over there. Go ahead.
What is this? Like, did the Ignathids migrate in and out over the millions of years? Or is that the older Gigantoraptor would eventually become the last Oviraptor?
Right, so the question was, did caenornathids migrate around and between Asia and North America especially? I think it's important to remember that when we refer to like North America and Asia as being different places, that's modern geography. And if we use late Cretaceous geography, that's one place. So it's probably much more continuous distribution of a lot of these animals across. And we actually do know, for instance, in rocks older than the Hell Creek, but not too much older, in the wetter parts of East Asia, like Siberia and the Russian border with China, that region, the dinosaurs there don't look like the desert dinosaurs we're used to in Mongolia. And instead it's what? Tyrannosaurine, tyrannosaurs, centrosaurine, ceratopsids, various types of hadrosaurs, both lambeosaurines and hadrosaurines. In other words, it's the same sort of dinosaurs we get in the Hell Creek and the dinosaur park and so forth. So it probably was much more continuous distribution throughout these regions. And you want to get really technical here? I think soapbox to them. Yes, quantification of biogeography is awesome, but how do you demonstrate a zero? How do you know when a group is not present in a region? Yeah, so we get to test positives. And some of these techniques really assume that when we don't see something, it's not there. And I personally have some issues with the logic behind that. But that said, the vast majority of people who do biogeography are perfectly happy with that technique, so listen to them. But I'm definitely with soapbox on. So you had a question over there, yeah.
Hello? Okay. So my question is, you actually sort of answered it earlier, how you, the age for Gigantoraptor.
Right.
I thought I read or saw something from Michael Pittman saying that Gigantoraptor, the specimen that they have, might be a juvenile or something. I'm not really sure.
That could be. Pittman would be the person who would be definitely involved in that research. And like I say, none of us know everything, even though I like to pretend I do. But I don't. I am publicly admitting it for everyone to say, I don't know everything. Okay, so there could have been a paper that I forgot about. But, or it may not be published yet. But it could be, and that's scary. Because, Gigantoraptor as it is like an Albertosaurus, Gorgosaurus sized animal. So maybe if it's still growing, the adult is T-Rex sized or more. You know, if you're not an apex predator, you know, you don't have to chase down your food. You know, if you're eating, well, as I said, you know, it's probably eating plants and also small-bodied animals, but to it, Protoceratops is a small-bodied animal. Yeah, so good question. Yeah, that would be really cool. Yeah, right there, Bianca. So we're Oviraptorosaurs of that giant-sized social animals. That's a good question. It's hard to say. Many of the Oviraptorosaurs do have prominent crests and so forth. And although there are, as Evan showed, there are other reasons to have crests, biomechanical ones. So to be fair, but often those are for some form of social display, so that at least on occasion, they're acting together in groups. Maybe not 24/7, and maybe not, you know, more importantly, maybe not 12 months out of the year, but at least sometimes. But there's a lot of, particularly for rare dinosaurs, a lot of questions when we have a very small sample size. We'd love to know the answers, but we don't have the evidence yet. Yeah, and then back there.
No, so you want to ask your question?
I was curious if they've ever figured out the purpose for the Tyrannosaurus' short arms.
The purpose for the Tyrannosaurus' short arms. My answer would be, it's kind of clear they're not doing too much with it as an adult. Because if you're going to reduce arms, that suggests that selection is saying they're not necessarily critical. But as younger ones, they might still be important. Plus, they could still be useful in display. I know it'll look goofy, but you know, yeah, because there are no animals that do goofy things. It would seem to be difficult for them to use them in prey acquisition because there's this enormous head with one of the most powerful bites ever evolved getting in the way. But you know, that's the thing. If you come up with the right research, maybe you'll come up with a solution to that. So yeah, 2 more questions. Okay.
Do you plan to work with Dr. Carr anytime soon again?
Oh, do I plan to work with Carr again sometime soon? When the right project comes up, absolutely. We've worked together on a couple, mostly on response papers, actually, because we both see something out there that we go, oh geez, this looks bad. Science works by reciprocal illumination. And therefore, when people propose ideas, it is incumbent on other researchers to sanely and soberly respond to them in the literature so that future generations can look at alternative ideas and come to the proper solution. Is that diplomatic enough? Okay, so, yeah. I work near DC, okay? So, so one more question? Yeah, back there.
Yeah, I had a question regarding niche assimilation.
Yes.
So you've talked about it within Tyrannosaurs kind of acquiescing the medium predator tier within the L3.
Right.
But I've also noticed I'm doing work on a raptor project right now for
Right.
school. And raptors make up a really small percentage of the L3 in terms of small predators. They make up like 2%, I think,
Right.
of all. Like, do you think that the even smaller Tyrannosaurs could have had a role in making their numbers so like small, or is that just their bones suck?
Right. So the question was about the question was about, you know, I've written before about ontogenic niche assimilation in tyrannosaurids, and that the medium-sized tyrannosaurs may have acquired the niche that at one point occupied by the mid-sized theropods, which were the tyrannosaurs actually back when the allosaurids were the dominant group. But he was asking, what about the smaller body size? Because although raptor dinosaurs, dromaeosaurids, are present, they're relatively rare, at least in our current samples, in places like the Hell Creek. I could say as much as was in an abstract. That's, I think, fine to say. There is work in progress by Dr. Schrader looking at feeding in younger, and ontogenetic changes in feeding in Tyrannosaurids. And it looks like different stages are feeding on different food elements in the ecosystem. And the ones that are comparable in size to the smaller dromaeosaurs don't look like they're eating small-bodied dinosaurs. And so I think at that point there actually is a niche partitioning going on between something like a Caroraptor, which is probably going after small-bodied dinosaurs and lizards and so forth, and the small Tyrannosaurs, which are going after other things. I don't think that they're necessarily feeding on the same types of animals, and certainly they're not acquiring the food the same way. That's an important aspect of their niche partitioning, is that the way they would get food would be radically different. Why are you kicking me? The gates of a Tyrannosaur, that's not doing anything. And the raptor leaps on.
All right, thank you, Dr. Holtz.